Experience in big in distributed systems and in the IoT market. I can share with you some of the use cases or how you can apply distributed frameworks such as Spark, Flink, and Ignite to solve the cases for IoT applications and services. How you can build an infrastructure that will be able to process all the workloads coming from your smart meters, from your smart sensors, from your edge devices deployed in factories or in plants. And the agenda for today is pretty simple. So first, before we start diving into the way how a problem can be solved, let's take a look what are the demands that are coming from IoT-empowered applications and services. After that, when we know these demands, I would introduce a high-level software stack that you as an architect should keep in mind. It's not the detailed one. It's not will be a breakdown, but it's something that the main building blocks you will have in your IoT solution or project. And after that, we are going to drill down on every module of this stack. We are going to look into device operating system or real-time operating system that is running on your edge devices. And to make things clear, an edge device is any device such as smart meter, sensor, smartwatches, everything else that is running on a constrained device and gathers measurements, information around your environment or around the field of the device applicability. Also, as you will see, there are different additional layers that are used in this architecture, such as data collection and enrichment layer. And for sure, we are going to use some data storage, some distributed storage, which I call hybrid transactional and analytical platform. And finally, when we come up with our HTAP platform, we want to be sure that that platform gives us enough APIs needed to build powerful applications on top of it. And usually, I end up every my conversation, every my presentation with a demo, and that meeting is not an exception for us. So at the end of this talk, I will show you how you can quickly create a simple application using Apache Ignite, Apache Spark, and transmit some data, stream some data into the cluster, and process it in real time. Well, as for the demands, the first demand that is pretty crucial for the IoT space is real-time processing. Oh, okay. Well, yes, the first one is real-time processing. And here is we mean that for some of the applications in the IoT realm, it's absolutely critical to be sure that all the data, all the measurements that are delivered to your software stack can be processed and received in real time. Just imagine that your software is running on some automatic driving car, and that car is usually equipped by a variety of different sensors, and it's a critical requirement to be sure that every measurement, every information that is delivered by your sensors is processed in real time. If you cannot meet this requirement, you can get into a car accident, and for sure we want to avoid this. The next requirement is how your platform is brought in terms of APIs. IoT developers, if we are talking about the back-end developers or high-end developers, the guys who are writing back-end software for your IoT solution, they also want to use common APIs like SQL, like key value operations. And what's else specific for IoT is if you invented some project that transmits your location, your proximity, then also you want to store the data in so-called geospatial format, and it will be beneficial if your platform supports geospatial data and APIs out of the box. The next thing is analytics. So for some of the products, it might not be a requirement, but for the rest, when you want to understand what's happening to your system or what's happened to your smart meters deployed in some factory a day ago or a week ago, you want to execute some analytical workloads. And most likely you will be executing nowadays, you will be executing them in parallel to the operational workloads, in parallel to the new information that is arriving to your software stack. And considering this, nowadays high availability became not just a nice feature to have, but a sort of a requirement. A lot of their projects, they want to be sure that whatever happens to my system, whatever happens to my architecture, I want to be up and running unless the whole data center goes down. But even if the whole data center goes down, there is a solution, right? You can have several data centers that work in parallel. And that's all about high availability. And finally, close to the high availability requirement, we have simple scalability requirement. That implies that first, we want to invest in such a solution that allows us to scale out gradually. So probably at some point in time, we are going to start with hundreds of meters, smart meters deployed somewhere, but all the time we want to scale out. We want to deploy thousands and dozens of thousands of meters. And our software architecture has to react accordingly. It should be simple. It has to be simple to scale out your existing software. And based on these demands, actually, we can take a look at this from this IoT software stack perspective. Starting from the bottom. First, if you're going to create your new IoT solution, first you need to deploy some edge devices like smart meters somewhere. And those smart meters, they also have to be programmed. You have to develop applications from them, software. And usually there are special type of operating systems and APIs that are developed for this sort of devices. If your device is powerful enough and you can run Linux operating system, embedded Linux on it, then you're good to go. You can install Linux and you can use POSIX APIs provided by that operating system. But usually all these edge devices, they are running on constrained hardware. And under the constrained hardware, I mean the chipsets that have around, let's say, that have dozen kilobytes of RAM and a couple of megabytes of flash. This is all they have. But that space, that amount of memory is enough, to install a real-time operating system on it and to develop applications that will gather different metrics surrounding the smart meters and transmit all this information back to your distributed storage and back to your software stack. On top of this, the next layer, which is called data collection and enrichment, usually this layer interacts with your smart devices. In this layer, you're going to connect to your smart devices, pull information from there, or the smart devices will push the information to this layer. You can enrich this data, meaning that you can take the raw data and transform it, adding something useful, adding some payload that is needed for your application. And right after that, right after you update it, right after you receive the data, you want to store it somewhere. And for big deployments or for the deployments that are supposed to scale out over the time, we want to store this data in a distributed platform, in a distributed database. And we don't want this distributed storage or database to be only SQL based. I want to interact with this storage using another APIs that are needed for my application. And this is why we are looking here into the so-called HTAP platforms or new SQL solutions. And that platform will be capable of storing the data in a distributed fashion and will provide you a variety of APIs that your application can benefit from. And today I'm representing Apache Ignite Software Foundation, and we are going to discuss the software that perfectly well fits to every layer depicted on this diagram, and all this software belongs to Apache. The bottommost layer here is I will briefly introduce you to Apache Minute. It's a real-time operating system this is actually the first and the only one at the moment real-time operating system that is available under Apache 2.0 license. As for the next layer, data collection and enrichment, here we have much more options. For the data, for the initial data processing and receiving and transformation, we can use Spark, we can use Kafka, we can use Flink. And today we are going to briefly look at Kafka. We are going to look at Spark and Flink. And I will show you during the demo how you can wire up together Ignite and Spark. And Ignite is going to be used as our distributed computational platform and our distributed storage. On top of, once you use Ignite for this purpose, your application will be empowered by a variety of different APIs. And today I'm going to show you some of the APIs that are useful for the IoT use case. We're not going to explore the whole platform because it would take a lot of time. I just want you to learn something that is specific for the IoT applications. Okay, now let's take a look at every building block from here in more details. So first, Apache Minute. What's so special about this operating system? First, this is open source real-time operating system that really can run on a constrained devices, on the devices or microcontrollers that are empowered by Cortex-M processors, CPUs, for instance. And if you to give some, basic understanding on this, a microcontroller usually is a small chip that has a CPU, RAM, flash, and sometimes networking components embedded. And you usually take this chip, this small chip, and build your smartwatches, your smart meters using that hardware. And once you construct it, once you assembled your hardware, you can flash Apache Minute there and use the rest of the APIs it supports. For instance, you can write standard networking applications. You can communicate to your backend system using Wi-Fi, Bluetooth, and networking protocol, and utilize TCP/IP or UDP. At the same time, when you need to update your software, first Apache Minute, as many other real-time operating systems, they guarantee that the data that is going to be flashed, the software that is going to be flashed into the hardware, that will be secured. So you can define some security policies to double check that nobody else, rather than you, can update the software on your hardware. And speaking about the updates, modern real-time operating systems, they do not, force you to come to your factory or to the plant where your smart meters are deployed, or Apple doesn't require you, to deliver all its smartwatches back to the office if they want to update the hardware, software. All this stuff can be done remotely. And you, as an IoT architect or IoT developer, you also, once you install Apache Minute, you can update Apache Minute version and the version of your software remotely from your office. The next layer, data collection and enrichment layer. That's layer, so as I said, it directly interacts with your edge devices. So usually you can connect to your edge devices using different networking protocols like Wi-Fi, Bluetooth, depending on the scenario. And once you connect to your devices, you can utilize Spark streaming functionality or Flink streaming functionality to receive initial data from there. You can, as you know, you can scale out your Spark cluster, for instance, depending on the workload coming from your smart meters. And later on, once you receive this data, you can process this data in parallel, enrich this data with additional information. And right after that, when the initial pre-processing of the data is done, you can move it on to your final storage, to your distributed system, where the data will be spread out across a cluster of machines And on top of that system, you can write additional applications that can do some useful thing with that. Okay, and if to talk about that platform, about Ignite as our HTAP platform, as our distributed storage and computational database. So actually, Apache Ignite is a memory computing platform that is durable, always available, and provides powerful SQL, key value, and other processing APIs. So at the core of this system lies so-called memory-centric storage. The memory-centric storage implies that the RAM, main memory, is treated not as a caching layer. It's treated as one primary storage, at the storage where your data as well as indexes will be kept by Ignite. At the same time, the memory-centric means that you can still use disk as your secondary memory tier, just for the sake of the durability. If you want to be sure that if some bad happens to a cluster, imagine that your whole data center goes down and you for sure don't want to lose the data. But if you enable this persistence, if you enable Ignite native persistence for sure, then you can be sure that after the cluster restart, you will not miss a piece of your data. All the data will be persisted on disk and you can start working with your data right away. So Ignite native persistence is tightly integrated with the overall memory architecture, and usually it stores the superset of data on disk, and you can have as much data in RAM as you can afford. So, and at the same time, you can persist the data on third-party databases or storages like NoSQL databases like MongoDB, Cassandra, or relational databases. It's up to you. But there are some of the differences between Ignite native persistence and third-party persistence. So if you are interested in this, then I'll be happy to elaborate more on this at the end of our talk. But okay, and all this storage is distributed, right? So all this memory is available across a cluster of machines you have, and once you have all the data and indexes in RAM, you can leverage from the variety of APIs provided by Ignite, like SQL, key value, MapReduce framework, which we call compute grid, machine learning, and other capabilities. If to look into this distributed storage, in reality, this distributed storage is a key value database. So the same hash table, so we all know how to work with hash tables, right? So every hash table consists of several buckets. And here is we are dealing with the same hash table, with the only difference that every bucket belongs to a specific cluster node, specific cluster machine of Ignite. And we call, in Ignite, we call these buckets as partitions. Some other products call these kind of buckets as shards, when people use sharding technology to spread out the data. And for sure, once you spread out this data evenly across the cluster of machines, you automatically get, you can automatically load balance the workloads. So every API call that comes to your application, depending on the data locality, that API call can go to one cluster node or to another. And this is how you can scale out your overall data storage, and this is how you can so-called scale out your workloads by just adding new nodes to your cluster whenever it's needed. The next, so speaking about the APIs, so since that's the key value storage, probably the fastest way possible to interact with the key value based storage is to use key value operations. So if you know an ID of your, let's say an ID of your smart meter, and you just want to get information about this smart meter, for instance, where it's deployed, in which geographical location, then you just can take this ID of the smart meter and set a query to your cluster. And then we can take this ID and we can identify precisely where this information is located. Because for every ID, we can calculate a primary node that stores the data for this type of record. And if you execute millions or hundreds of thousands of such queries in real time, you can see that all these queries will be sent to different nodes. And this is how you can distribute your workloads by using simple key-value operations. The other API that is useful for IoT applications is SQL. It's required when you want to execute some advanced queries, like you want to see what was the highest temperature reported by your smart meters, or how many smart meters failed throughout the previous week. All this information is easy to retrieve using SQL language, right? So, and if you don't want to invent your own language, Ignite offers you full-fledged SQL APIs on top of it, and even more so, quite often Ignite is used as a just full-fledged SQL database, simply because you can execute not only standard select queries, but you also can update data using operations like inserts, update, deletes. If you want to configure your cluster data sets, you can use create table commands, you can define indexes and redefine indexes in real time. And all these operations can be done not only from Java, .NET, or C++ libraries that are provided by Ignite out of the box, but you connect to your cluster from your favorite tool or from your favorite language using ODBC or GDBC drivers. This is what we provide here. The next interesting thing is Compute Grid. So actually, Compute Grid is Ignite's map-reduced framework. So the same framework you're accustomed to use in Spark or in Hadoop. So the idea is the same. You write your computation logic, and you send this computation logic to your cluster. And depending on the type of this computation logic, it can be just randomly distributed across a cluster of machines, as we see here. And if you apply different load balancing techniques for this logic, for different calculations, then Ignite can, prefer underloaded cluster nodes for new jobs calculations rather than overloaded nodes in your cluster. Speaking about Spark, so if you use Ignite and Spark together for your IoT solutions, Spark usage is not limited to the streaming part. It's not limited only to the data processing and enrichment step. If you're kind of advanced Spark user and you prefer to keep working with Spark APIs, Ignite is integrated with Spark. So actually what you can do, you can connect from your Spark applications to your underlying Ignite cluster and work with the data stored in Ignite using Spark RDDs APIs, for instance. So I will show you today how we can connect to the Ignite cluster from Spark, get access to our data sets stored in Ignite cluster from Spark shared RDDs, and how we can, work with this data using that already known Spark API. Yeah.
Is Ignite on AWS?
Say?
Is Ignite on AWS?
What is the Ignite database?
Is Ignite on Amazon Web Services?
Ignite, so Ignite can be deployed on premise or in any cloud environment. It doesn't matter. So you can go and deploy Ignite on AWS, Microsoft Azure, or Google Compute Engine, or as I show you today, you can deploy your Ignite cluster on your local laptop. It's up to you.
So is it part of EC2 or like VMware?
No, there are two things. First, Ignite is available on Amazon Marketplace, so you can install it from there. Or you can just go ahead and download Ignite from Ignite site and upload it to your Amazon cloud and set it up there.
And does it the persistent storage, does it work with S3 as well?
There is no. So the question is, does Ignite support S3 storage? So there is no any support out of the box. But if you want to use S3 as your persistence layer, there is a straightforward, like 5 methods API that you need to implement. That's it, if you want to use S3 as your storage. But most likely you don't need to use S3. You can use For instance, if you use Apache Ignite persistence and you need to do some backups copy of your data, then S3 is a good place to store your backups, something like that. But there are a lot of options how you can use Ignite and deploy it on AWS. Good? Disappeared.
Yeah, I just said the walk over.
And finally, for the scenarios when your IoT solution, when your IoT applications need to do some more than just advanced lookups using SQL, or it's even not enough for you to utilize our MapReduce framework, then you can take a look at the machine learning grid. So it's a set of machine learning APIs that are being developed on top of Ignite. And actually, there is a reason why we decided to initiate this development, because we talked a lot to our customers and users, and they shared the idea, guys, we already use your compute grid, your MapReduce framework, and we use your distributed storage capabilities and build our own machine learning applications on top of it. Why don't you go ahead and implement your own? Why don't you simplify? Why don't you facilitate this part from your side and develop these APIs on Apache Ignite side? And now we have some machine learning enthusiasts in our Apache Ignite community that already developed a distributed core algebra framework on top of Apache Ignite distributed storage. And they are working on a variety of different essential machine learning algorithms such as k-means clustering, linear and logistic regressions, decision trees, and so on and so forth. So this is something that is new. That component is available in beta. And I'm just mentioning it because if there is someone of you, because machine learning is still required and used in IoT, and if there is someone of you who is passionate about machine learning, if someone of you wants to implement some distributed version of a well-known algorithm, just stop by Apache Ignite community. We will welcome you, and we will help you to make you successful, and you will be able to contribute to this library, making something new, useful, and building your skills in this direction. Well, I think that is enough about APIs, about capabilities. So all these capabilities, I just picked only those capabilities that are related to IoT, for IoT scenarios. And speaking about, it's obvious why we should use Spark or Flink, right, for these sort of scenarios. But why should we rely on Apache Ignite? So speaking about Apache Ignite, so it has a lot of usage use cases. Most of them fall into the financial services market because of the guarantees, strong consistency and transactional guarantees that are provided by this platform. But at the same time, there are, so some of the companies such as Silver Spring Networks, ThinWorks, that already use Apache Ignite exactly for the IoT scenarios, using Apache Ignite as a distributed storage and computational platform. For instance, if to quickly look at this use case that was shared by Silver Spring Network with Apache Ignite community, what they did, they are using GridGain cluster. GridGain is an enterprise. So GridGain uses Apache Ignite, builds on top of Apache Ignite, and provides enterprise-level features on top of the open source functionality that is available for everyone if you download Apache Ignite. So if to think of GridGain, it's the same Apache Ignite with extra features on top. And Silver Spring Networks uses GridGain in production because of the additional enterprise features required. And what they did, there is a special platform developed in-house, and that platform helps to track information about many electricity pillars deployed nationwide, and depending on the load in different regions or states of the United States, they can move the overall memory, the overall electricity usage from one region to another. If they face the situation when in one region we see overconsumption of the electricity, but in the other region we see that the electricity is not consumed that well, they can move all this stuff over the wires. And they have a kind of an easy problem. At some point of time, they could not meet their SLAs. And the architecture was built on a classical relational database that was used as the storage and served and processed all the APIs, all the calls. But once they are moved to the GridGain and Apache Ignite, the distributed cluster, they were able to deploy dozens of millions meters and all these electricity pillars nationwide and process all the data and all the measurements in real time. This is what they could achieve with this type of architecture. And now the part that I like more. Let me show you quickly a quick demo. So I want to demonstrate how you can quickly start with Apache Ignite and Spark. And I'll ask Laura to facilitate me with this because I need both hands. So first thing, here is I prepared a simple application. I'm going to start a couple of Ignite cluster nodes in my local laptop. It's a really straightforward operation. All I need to do is to call this API method and pass Apache Ignite configuration. This configuration includes just basic parameters such as IP addresses of my cluster nodes so that they can find each other and form a single cluster of machines. Okay, let me start several nodes. Well, we have the first node up and running. We can see that presently there is only one node, cluster node in my local cluster. And here is we are waiting for the second one to join this party. Okay, and now we have two cluster nodes. I have two Apache Ignite nodes on my local laptop running. And the next thing would be the following. Let me just first show you how you can monitor the state of your cluster. For that purpose, Apache Ignite community developed a special management and monitoring tool. It's called Apache Ignite Web Console. This one is named GridGain because you can take this Apache Ignite Web Console and deploy on your own hardware, and you can change, the logos, all the parts you need. So this console is deployed on GridGain side. You can also use it for your testing purposes or even in production if you're ready to do this. I'm going to use it for the sake of the demo. So here is, let me double check that I can connect to my local cluster from this console. Yes, so I see my two cluster nodes that are running on my laptop. I'm not going to use the persistence. All the data will be in memory. I don't care. And also, once I started my cluster nodes, I created two caches. So in terms of Ignite, we use the term cache. It's not just a cache of data in memory. It's the same as a table in the relational databases world. But in the distributed world, in the world of Apache Ignite, a cache is your unique table, distributed table, where you store your data. And we are going to have two caches. First one will store information about different sensors deployed somewhere and the temperature reported by these sensors. Okay, now it's time, to start doing something useful with that. And let me show you how you can work with your cluster from Spark as a Spark application developer. So here is my simple Spark application. What I'm doing, I'm preparing Spark configuration. I'm creating streaming context. I'm going to use a Spark streaming framework. And after that, I need to do some basic configuration parameters needed for Spark to talk to Ignite. And here, as you can see, those two caches that are already configured in our cluster. And I'm going to connect to those caches by means of Spark RDD APIs. This is what I'm doing in these 2 lines. And finally, the next, we are going to do 2 things. The first thing is we are going to preload our sensors cache with some dummy data. For instance, what I'm going to do, I'm going to create several sensors and install or deploy them in various geographical locations, randomly picking latitude and longitude. Once I've filled in this information, I'm going to save this data into the Apache Ignite by calling this save pairs method. That's the standard method available for you on RDD APIs. Once this is done, I'm going to receive some sample temperature measurements from this localhost port number. I'm going to process these measurements. That will be measurements of the temperature reported by one of the sensors created before. And once I do all these transformations, such as I want to add a timestamp to every measurement, I'm going to save all this data, transmit all this data constantly to my Apache Ignite cluster in real time. So Spark is going to receive the data, process it, transform, and send it right away to Apache Ignite cluster. And while this data is going to be processed and sent to Apache Ignite in real time, I want to execute I just want to see what's going on. I want to execute, for instance, select queries over the data that is being streamed into my Apache Ignite cluster. And that query, we are still using Spark. We are going to, for instance, here is I want to see what was the maximum temperature, how many sensors we have in my cluster that reported temperature in this range from 70 to 100 degrees. That's a simple query. Okay, let's start this simple application. So now Spark is doing his basic setup routines, and right after that, the Spark is going to connect to Apache Ignite using special client connection. This is why you see Ignite logo here. So Spark is connecting to Ignite using special Ignite API. But you just need to do just valid configuration. You don't need to do anything else, just to provide configuration where your Apache Ignite cluster is. That's all what you need to do. Okay, so we are connected, and here we see some strange errors. This errors report say us that we do not receive anything from this localhost port number. No any temperature measurements are transferred to us. But to do this, there is another simple Java dummy application. So instead of bringing any edge devices here, I wanted to simplify the task for us. So I just created a simple Java application that opens up the server socket connection. And once our Spark connects to this application, which in real world will be a mesh of your sensors deployed somewhere, we are going to create different temperature measurements, random measurements for random sensors deployed in our cluster, and write them into this socket connection. And then the Spark will do the rest of the work. Okay, let's start this application. Okay, we see that the Spark was connected to the cluster. And now if we scroll down, we should see that that exception disappeared. And this is the result set reported by our select query. So the data is being received and processed in real time, processed by Spark, sent to my local Apache Ignite cluster, and this query is executed over the data that is on Apache Ignite. This is how many sensors, the IDs of the sensors that reported the temperature in the range of 70 and 100 Fahrenheit. At the same time, we can do some more advanced lookups. Here as we can see that our cluster data is being grown, so we keep putting more temperature data into my cache. What I can do right now, I just can do some more advanced queries over the data I have in my cluster. So for instance, let me see what was the maximum temperature reported so far by my sample application. And it turns out to be that the maximum temperature was 109 Fahrenheit. Or in Apache Ignite, you can execute not just simple, SQL queries. You can also execute distributed joins, joining the data that is also stored in different cluster machines. And using this type of join, I want to find out the maximum temperature reported by the sensors located in the boundaries of the United States. So these are the boundaries of the continental part of the United States. And we are going to take a look at what's going on with the temperature in this part of the world. Okay, we also can keep executing this query for every 2 seconds. And for now, we can see that the maximum temperature reported so far was 97 Fahrenheit. Okay, actually that's all for the demo. And before we move on to the Q&A session, let me advertise you the In-Memory Computing Summit. It's a conference that will be that will take place in San Francisco in the end of October. And here is if you actually want to learn more about different in-memory technologies, about distributed systems, not only about Apache Ignite for sure. There will be plenty of folks who are developing Apache Ignite, but also you can learn a lot about different solutions of vendors such as Hazelcast, Redis, MemSQL, VolDB. So if you want to discover more about all these distributed systems and memory technologies, I highly encourage you to stop by this conference. And actually, you can check out whether you are lucky or not. GridGain is raffling 2 tickets per week for this conference. So I'm going to share this presentation, and then after the talk, you can go to this link and try to sign up for this raffle. And finally, thanks to the Laura who helped me out today. So if you want, today we covered all the features of Apache Ignite that are available in open source version. But if you want to learn more how to how to set up data center replication, or how to set up advanced security, how to do data backups using Apache Ignite cluster, then you can discuss all these questions and topics with her. So, having said that, thanks guys for attending, and now I'm open to your questions.
Thank you. In the demo, you created the RDD from the Ignite, and then you call one of the functions to save. And when you call the save, what happened? So the RDD data still resides in Ignite, or they are transferred to the Spark cluster?
Yeah, it's a good question. So once you call this method, RDD save, we are going to use special type of Ignite own streaming technology that will take all the tuples stored in this RDD and will push them into the cluster. Once the data is stored in the Ignite cluster, it will be garbage collected by Java virtual machine where your Spark application is running. And also, when you want to get this data back, or for instance, when I showed you how you can execute SQL queries from Spark, that SQL query was executed over the data that is in Ignite. So Spark did not go to Ignite. It did not take the data from Ignite. It did not preload the data back to Spark. So all the queries operate over the data that is already in Ignite. So you don't need to move the data back and forth from Ignite to Spark. So yeah, so Ignite here is Spark treats Ignite here as a distributed storage, such as Hadoop or something like that. The only difference here is that, for instance, Hadoop is a disk-based storage, while Ignite is used as memory-centric storage that can keep data both in memory, in RAM, and on disk.
Right. So my concern was, did you duplicate the data between Ignite and
No. We do not duplicate the data. So once the data is pushed to Ignite, It will not be stored in Spark.
The way to do this for RDD operation, the data still resides not.
Yeah, correct. The data is always in Ignite in this configuration. Any other questions? Not yet. If you have, so I'll be here around. So if you want to discuss something, you can talk to me. I can give you more details on all the components we briefly discovered so far, or you can share more details on use cases related to the IoT or different other markets. Or you also can talk to my colleague to learn more about GridGain use cases. Thank you, guys.